All right, so now that we know how to plot points on a polar graph, it's time for us to plot some actual polar graphs. And I know you think that you've already done that, but trust me, you haven't. So just like plotting a couple of points on a graph using a quadratic equation doesn't mean you've graphed a parabola, so too, plotting a few points on a polar graph doesn't mean that you have graphed a polar equation. It just means that you've plotted a few points on a polar graph. So let's look at a polar equation. Polar graphs come from polar equations, obviously, and they're written in the form of r equals something involving theta. In this case, let's use 3 times the sine function of theta, which means I'm going to choose a theta value, calculate an r value, and then I have the ability to graph that on a polar graph and see what happens as I plot multiple points. So first, let's pull together a set of tools. I'm definitely going to want a bigger graph so I can see my values around the outside. And I'm going to want a calculator. I use a graphing calculator. You're welcome to use a graphing calculator. I use a TI-89. You can use any one you want. And if you don't have a graphing calculator, that's fine. Any scientific calculator that will give you approximate trig value will be sufficient. So I'm going to make some configuration changes. If you're using a graphing calculator, this will be important. If you're using a scientific, it depends on which one you have, whether or not you have to configure it differently. So first, let's get it turned on. I'm going to be working in polar graphing. So I want to go to the mode. And here where I have my graph type, I'm going to choose, rather than function, I'm going to choose polar. Polar graphing is also done in radian measure, so go ahead and switch that out. And then I'm going to want to change, the next setting I'll get to in a minute. So notice when I go to insert or input this equation now into my y equals, I don't get a y equals, I get a r1 equals. Also notice that when I go to put in my values, this says r1, meaning just the first polar graph in r of theta. I have to use theta. I can't substitute x like I could do before when I was dealing with trigonometric graphs. So let's put in 3 sine theta. There we go. All right, so now I'm ready to work with my equation, and I can use all of the other graphing tools of a table, which I'll use in a moment, and all of my other operational tools in my calculator to go with this function or with this equation in r and theta rather than y and x. So just like we did when we were learning to graph other kinds of equations, we want to start by creating a data table, and then later we can look at how to use parent forms of a graph to predict the shape. The independent variable that we're free to choose is going to be theta. So we'll plug in values of theta from the polar table, and we're going to plug that value into our equation to find out what r equals. So for example, if I choose theta equals 0, which is the smart place to start because that's the beginning of a polar graph, theta equals 0, the sine of 0 is 0, times 3 is 0. So when theta equals 0, I'm going to get the point 0, meaning, I'm going to get the r value of 0, meaning that when I plug in this angle, I get an r value of 0. So I just get a point right on the pole. The next angle I come to, well, and the polar graph is 15 degrees. I can certainly use 15 degrees. I don't really want to. I want to use my common angles. So the next one I come to is 30 degrees, or pi over 6. And pi over 6, or the sine of pi over 6 is 1/2 times 3 is 3/2, or 1.5. So I move to the next angle, which is 45 degrees. Now the sine of 45 degrees is root 2 over 2 times 3 is 3 root 2 over 3. So let's back up here to my angle of pi over 6. When I'm looking at the angle for pi over 6, well, let me look again. Yep, that's the right one. Pi over 6, I can tell that 1.5 falls exactly for this angle on this line. And the reason is that I'm using intervals of 1/2. So this would be 1/2, 1.5, 2.5, 3.5, 4. And so 1.5 would be this radius right here. So I can plot this point. Easy peasy when my angle is pi over 6. When my angle is pi over 4, I get 3 root 2 over 3. But where is that? I don't know what that is. I can guess probably, but I couldn't guess close enough between 2 and 3 or right in this area. I wouldn't be able to guess. And so we don't want to use exact values when we're plotting these. Instead, I want to use my calculator to figure out what the value would be. So for pi over 3, I'm going to plug in 3 times the sine of pi divided by 3. And I want an approximate value. So 2.59. So now I can say 2.59. And that's much more useful for graphing. Here I am on my line, on my angle, pi over 3, and 2.59 is almost at 3. So right here. And last, well, not last, but next, pi over 2. This one's easy. Sine of pi over 2 is 1 times 3 is 3. So at pi over 2, I can plot the point 1, 2, 3. Now look at what my points look like. They're kind of funny looking, aren't they? They're actually making 2.59. This point is out of place. You probably saw me make that mistake. 2.59 means almost 2.6. So at 60 degrees, I'm actually just going to be a little bit beyond 2.5. And so really, if you look at this, it's going to sketch out, had I taken every value in between, it's going to give me this little half circle. So what happens on the other side? Well, the next angle, common angle over, is 2 pi over 3. So if I put in 2 pi over 3, what do I get? Same thing here, only I'm going to come back and do 2 times pi over 3. Oops, I forgot to say, oh, there's my exact value, which is of no value. And so I'm going to put in my approximate 2.59. Look at that. I got exactly the same value for the reference angle pi over 3 in the first quadrant as I did for the reference angle pi over 3 in the second quadrant. And so what I actually get on this second side is a reflection over the angle theta equals pi over 2. This angle would give me a reflection to, let's see if I can find it here. There it is. This angle would give me a reflection to here. And so if I connect them, I would get a circle on the other side. All right, so, well, I get the other half of the circle, the half circle on the other side. And so the polar graph r equals 3 sine theta actually plots a circle with a radius of 1/2. Or 1.5, 1.5. That's pretty cool, isn't it? All right, so I intentionally didn't plot the 15 degrees intervals that gave me a couple of extra intervals on this graph because I want to show you another function that you can use on this graph. If you once you have your equation in your table, or excuse me, another function that you can use on your calculator. Once you have a equation entered into your calculator, you can use a table to evaluate these values. But the problem is it doesn't give you the values in radian measure or even in degrees and anything you can recognize. It gives you the values in decimals. So if I want to set up a table to work with this particular graph, I would have to be able to set up a table with forward steps or next points or next angles in the table being uniform all the way around. And that means I'm going to have to use pi over 12 or 15-degree angles. So if I set up my table to start at 0, right here, just like I started at 0 before, if I set my table up to start at 0, I can move here and tell my table then to increment forward at pi over 12 units. And if I don't know what that is as a decimal, no big deal. I can put in pi divided by 12. Enter. So now it's automatically going to give me all the multiples of pi over 12 starting with 0. So if I press enter and then go to the table, there we are. We can see my 0 value is at 0. And I'm going to do check marks just because it'll help. Then the one we don't have is at pi over 12 or 15 degrees, but that value is 0.77646, just under 1. So on this line, on this angle, I should have a point just less than 1, and look at that, I do. That intersects right there. That would be that point. The next point would be for pi over 4 at 1.5. I have that one. The next point would be the one I already calculated. And had I not calculated, 2.12. The next point at 60 degrees. The next point is going to give me this angle here at 75. So 2.897, or let's say 2.9, which makes total sense because right here is going to be just less than 3 because this was at 3. So the next point at pi over 2, I get 3 right there. The next point is at 100 degrees. I get a reflection across, just as I would have expected. Not exactly there though, huh? There. My next point, 2 pi over 3. My next point, 3 pi over 4. The next point, 5 pi over 6. These little numbers are hard to read. And the next point is at my 15 degrees reference angle, 0.7746, right here where it's expected. And so I've completed the circle without having to fill out my own table. I can use the table in my graphing calculator. So if you have a graphing calculator, you're welcome to use the table as long as you plot all of the points that show up on the table. That I've only gone halfway around my angles, right? I've only gone halfway around the circle that produces inputs for theta, but I've completed the circle, apparently finished the graph. What happens with all of these over here? Well, check it out. If I go down to here, right, to a 15-degree reference angle, oh, I'm sorry, I just went to pi. I don't know why the calculator gives me ellipses instead of 0. Maybe because the calculator is thinking that at pi you get -0, and so you get an ellipses, because sometimes it has, these TIs have weird evaluations with negatives and 0, or with negatives. So anyway, it just says that I've got the same point here. Then the next one down for the 15 degrees, this is this angle, it's right here, right? This angle 15, but it's a negative 0.77. What do we do on this angle with a negative radius? We just push it right back over here to where we already were. And then looking at one more just for clarity, the next angle, which puts us at our 30-degree reference angle, says -1.5. So on this angle, -1.5 would put us here, but the negative says, nope, just goes straight across to here. And so Really, on the back side or on the second half of the circle, we only get a repeat of what we already had. And so polar graphs often have domain restrictions. In this case, we would only want to look between 0 less than theta less than pi, only because, or 0 less than or equal to theta and probably less than pi. So then we wouldn't have to continue around and just duplicate our effort to get only the exact same thing. Okay, whew, that part is done. Not all polar graphs create circles, but the first ones that we work with will. But the circles can be created in different places. And let's look at those because they give us some indications of symmetries that we want to look at or be able to identify. Because notice, and I did this, you wouldn't necessarily have known to do this, but because I know that the sine equation for polar graphing is symmetrical about this line or this angle pi over 2, then I knew once I got half of it done that I would be able to just finish it out using points of symmetry. It'll save you a lot of steps if you know the symmetries in polar graphs. So let's talk about them a little bit. Not specifically, but in general. If I have a graph that has a symmetry about the angle theta equals pi over 2, so the angle pi over 2, then I can say that I have a symmetry about theta equals pi over 2. It's that easy, it's that direct. I also can say, or I know, I can reference it by saying, showing the symmetry, that if I have a point r theta on, I got hung up for a minute, on my graph that is symmetrical about the angle theta equals pi over 2. Oh, this is a lot of vocab, a lot of hard changings to say. Then if this point is on my graph, then symmetry dictates that so too is the point r, same radius, right? From here to here would be the same radius, r, and theta, though, in this case, is going to be pi take away theta. So we're going to use the reference angle, pi minus theta. Does that make sense? You have theta on this side. To get to the same angle on this side, you have to have pi take away theta using the reference angle. Okay, if you have symmetry, around the x-axis, like this, we actually have a special name for this. We say that we have symmetry about the polar axis. For obvious reasons. This is the polar axis, so the symmetry is about the polar axis. And labeling for that is that if you have a point, r theta, so radius and theta, then you also have a point guaranteed at minus r and minus theta. Or minus r, right? This angle. So it would be pi minus theta. This is the correct, I jumped ahead of myself a little bit. So this would be the angle pi minus theta, just like on this one, but minus r puts us forward into minus r. And then the last symmetry that we can look at is symmetry about the diagonal. And this is called, we used to call it in polynomials, symmetry about the origin. So what do we call the origin in polar graphing? This is symmetry about the pole, or polar symmetry. And the point that we would look at here is if I have a point r theta. Then I must also have the point r, so the radius is the same in both directions, but this angle is now pi plus theta. So polar graphs make these really cool shapes. This is just a circle. It's only the beginning. Polar graphs have really cool shapes. This one is a circle, and they have symmetries that help you make it easier to finish if you know the symmetry of a graph. If this is a half circle and I knew that the symmetry was about the pole, I would know to put a half circle on this side. If this was symmetrical about the polar axis and it was a half circle this way, I would know about the polar axis to put another half circle here. Those last two examples don't actually happen in polar graphs, not at least simple polar graphs, but it made the point for me about symmetry. So symmetry helps us not have to plot so many points. So does a graphing calculator that has a table function in it. And using the polar graph with 15-degree intervals all the way around, you can trace a table through and plot your points for your polar graph. Your first set of examples will be graphing, plotting points and graphing simple polar graphs, and then expressing or explaining the symmetry from what you see. Then we'll move on to some more complicated polar graphs. Oh, yay. But there's plenty of time for that later.